We are on a collision course with our neighboring large galaxy Andromeda, a system of several hundred billion stars. This collision will lead to a mutual descent, altering both galaxies in significant ways. The Andromeda galaxy, historically vital in showing that the universe did not revolve around us, has been the focus of astronomical study for over a century. It was Andromeda that proved the Milky Way was not the only galaxy, shifting our understanding of the cosmos. While much has been learned from Earth, advancements like the James Webb Space Telescope have provided new, shocking insights about Andromeda that we didn't foresee for an entire century. James Webb Space Telescope just received a terrifying signal from the Andromeda galaxy. Just over 100 years ago, the Milky Way was perceived as a faint band of light across the night sky due to limited technology that prevented the discernment of individual stars. Various beliefs about the Milky Way centered it in creation. This changed in the early 17th century, when Galileo Galilei used his telescope to observe that the Milky Way was not just a band of light, but a vast collection of stars, planets, and celestial objects. Galileo's work debunked the notion that the Milky Way was the center of the universe, revealing it as a sprawling expanse of stars. In 1750, English astronomer Thomas Wright hypothesized that the Milky Way was a flat layer of stars, including our solar system, a theory limited by the technology of his time. By the early 1900s, significant advancements were made in astronomy. In the 1920s, Edwin Hubble used the Hooker telescope at Mount Wilson Observatory to demonstrate that distant nebulae, including the Andromeda galaxy, were separate galaxies with billions of stars, fundamentally transforming our understanding of the universe. We are on a collision course with our neighboring large galaxy Andromeda, a system of several hundred billion stars. This collision will lead to a mutual descent, altering both galaxies in significant ways. The Andromeda galaxy, historically vital in showing that the universe did not revolve around us, has been the focus of astronomical study for over a century. It was Andromeda that proved the Milky Way was not the only galaxy, shifting our understanding of the cosmos. While much has been learned from Earth, advancements like the James Webb Space Telescope have provided new, shocking insights about Andromeda that we didn't foresee for an entire century. James Webb Space Telescope just received a terrifying signal from the Andromeda galaxy. Just over 100 years ago, the Milky Way was perceived as a faint band of light across the night sky due to limited technology that prevented the discernment of individual stars. Various beliefs about the Milky Way centered it in creation. This changed in the early 17th century, when Galileo Galilei used his telescope to observe that the Milky Way was not just a band of light, but a vast collection of stars, planets, and celestial objects. Galileo's work debunked the notion that the Milky Way was the center of the universe, revealing it as a sprawling expanse of stars. In 1750, English astronomer Thomas Wright hypothesized that the Milky Way was a flat layer of stars, including our solar system, a theory limited by the technology of his time. By the early 1900s, significant advancements were made in astronomy. In the 1920s, Edwin Hubble used the Hooker telescope at Mount Wilson Observatory to demonstrate that distant nebulae, including the Andromeda galaxy, were separate galaxies with billions of stars, fundamentally transforming our understanding of the universe. The Andromeda galaxy, also known as M31, has been observed since at least the 10th century, when Persian astronomer Abd al-Rahman al-Sufi described it as a small cloud. Al-Sufi's keen eyesight allowed him to identify Andromeda without telescopic instruments, a feat possible because Andromeda is one of the few galaxies visible from Earth's surface without special instruments. It wasn't until 1612 that Simon Marius provided a telescopic description, laying the groundwork for future astronomers. In 1764, Charles Messier catalogued Andromeda as M31, furthering its recognition. A major leap in understanding Andromeda occurred in 1864, when English astronomer William Huggins studied its spectrum, finding it different from typical gaseous nebulae, which was a pivotal observation. Andromeda is massive, with a mass estimated to be between 1 and 2 trillion times that of our Sun, and is thought to be about 10 billion years old, suggesting a complex history of formation through the merging of smaller proto-galaxies. Previously, astronomers thought Andromeda was significantly more massive than the Milky Way. Recent research has revised these estimates, showing that the masses of both galaxies are much closer than previously thought. The Andromeda galaxy's physical dimensions are larger than the Milky Way's, with a diameter of about 220,000 light-years compared to the Milky Way's 100,000 to 175,000 light-years, highlighting its vastness. One of Andromeda's fascinating features is its active galactic nucleus powered by a supermassive black hole with a mass between 110 to 230 million times that of our Sun. Observations using advanced telescopes, like the Hubble Space Telescope, showed 2 points of concentration in the Andromeda galaxy, with the brighter one slightly off the true galactic center, indicating intense gravitational interactions and the presence of a supermassive black hole. Andromeda also has an abundance of globular clusters, estimated at around 460, each containing hundreds of thousands to millions of stars. This abundance indicates Andromeda's history of galactic cannibalism, where smaller galaxies were absorbed into Andromeda, adding to its stellar population and diversity. Recent observations suggest that Andromeda may be transitioning from a typical spiral galaxy to a ring galaxy, a relatively rare type characterized by circular ring-like structures of bright young stars. Ring galaxies can form through galactic collisions, or when a smaller galaxy passes through the center of a larger one, making them unique among galactic structures. The impending collision between the Milky Way and the Andromeda galaxy is a cosmic event predicted to start approximately 4 billion years from now and will unfold over the subsequent 2 billion years. This grand encounter will culminate in the formation of a new supergalaxy, which has been informally nicknamed Milkomda by astronomers and enthusiasts. The merging process will be characterized by significant gravitational interactions and tidal forces, profoundly affecting both galaxies. As the Milky Way and Andromeda approach each other, their immense gravitational forces will begin to distort each other's shapes. This gravitational interplay will pull stars, gas, and dust from each galaxy, creating elongated tidal tails and triggering a series of complex gravitational interactions. The overlap and mingling of the two galaxies will not be a smooth process. Instead, it will be marked by chaotic and dynamic changes as their structures are gradually dismantled and reformed. One of the most dramatic consequences of this collision will be the formation of new star clusters. As the galaxies merge, the gas clouds within them will collide and compress, leading to bursts of star formation. These stellar nurseries will be regions where intense gravitational forces compress the gas to the point of collapse, forming new stars. These newly formed stars will often be grouped into clusters, enriching the new supergalaxy with fresh stellar populations. At the same time, the gravitational turmoil will cause changes in the orbits of existing stars. Stars that were previously in stable orbits around the center of the Milky Way or Andromeda will be thrown into new, more elliptical paths or potentially flung out of the merging system entirely. Some stars may find themselves ejected into intergalactic space, becoming rogue stars no longer bound to any galaxy. This redistribution of stellar material will contribute to the formation of new cosmic structures, and may result in an intricate web of star streams and clusters that blend the remnants of both galaxies. In addition to forming new stars and clusters, the merging process will also create massive complex structures within the new galaxy. The gas, dust, and stellar debris from both galaxies will mix and settle into new configurations, forming vast regions of star formation, spiral arms, and potentially new galactic features that are a hybrid of both the Milky Way's and Andromeda's original forms. These structures will evolve over time, influenced by the new dynamics of the merged galaxy. The supermassive black holes at the centers of the Milky Way and Andromeda will also play a crucial role in the merger. As the galaxies coalesce, their central black holes will eventually merge, creating a single, even larger supermassive black hole at the core of Milkomda. This merged black hole will be a powerful source of energy and will have a significant impact on the surrounding stellar environment, contributing to the new galaxy's dynamic and evolving structure. Ultimately, the merger between the Milky Way and Andromeda will result in a completely transformed cosmic landscape. The new supergalaxy Milkomda will be a colossal entity composed of the blended material from both progenitor galaxies. It will feature a rich tapestry of new star clusters, altered stellar orbits, and restructured galactic features. This process of cosmic evolution, driven by the collision and merger, will shape the future of the local group of galaxies and provide a fascinating glimpse into the long-term dynamics of galactic interactions. The merger will result in profound changes to our night sky and the environment on Earth, potentially affecting habitats, biodiversity, and climate. However, this process will occur long after humanity is gone, as our sun will evolve into a red giant and render our solar system uninhabitable in about 5 billion years. The merger of Andromeda and the Milky Way raises questions about the fate of our solar system and the formation of new galactic structures. The cosmic interactions will shape a new galactic environment, possibly with habitable zones for potential life forms, although vastly different from what we know today. The Milkomda galaxy will be a testament to the dynamic and ever-changing nature of the cosmos. The collision between the Milky Way and Andromeda, predicted to occur in about 4 billion years, will be a spectacle of cosmic proportions. It marks the culmination of a gravitational dance that began billions of years ago, when these two colossal galaxies first started their inevitable approach toward each other in the vast expanse of space. As the merger progresses, one of the key phenomena astronomers anticipate is the transformation of both galaxies' spiral structures. Currently, the Milky Way and Andromeda are spiral galaxies characterized by their prominent arms extending outward from a central bulge. These spirals are defined by the rotation of stars and gas around a central core, creating distinct patterns observable from Earth. However, as the galaxies draw nearer and their gravitational influences intertwine, these spiral structures will undergo significant changes. The mutual gravitational attraction between the Milky Way and Andromeda will distort their shapes, pulling and stretching their spiral arms into elongated tidal features. These tidal tails will be composed of stars, gas, and dust that have been pulled away from their original galactic disks, creating a chaotic yet mesmerizing display across the cosmic landscape. The collision will also trigger intense bursts of star formation within the newly forming supergalaxy. The interaction of gas clouds from both galaxies will compress and heat up, leading to the formation of massive, luminous star clusters. These clusters will become the nurseries for young stars, whose energetic radiation will illuminate the surrounding cosmic dust and gas, giving birth to new stellar populations. The merging process will not only affect the appearance of the galaxies, but also their internal dynamics. The gravitational interactions between stars and gas clouds will cause a reshuffling of their orbits and velocities. Some stars will be flung into more eccentric orbits, while others may be expelled entirely from the merging system, becoming free-floating rogue stars in the intergalactic void. Meanwhile, the supermassive black holes at the centers of the Milky Way and Andromeda will play a pivotal role in shaping the future of the merged galaxy. These behemoths, each millions of times more massive than our Sun, will eventually spiral toward each other under the influence of gravitational waves emitted as they orbit closer and closer. The final stages of the black hole merger will be cataclysmic, releasing enormous amounts of energy into space in the form of gravitational waves and radiation. This merger event will create a single, even more massive supermassive black hole at the heart of the newly formed galaxy, surrounded by a swirling accretion disk of gas and dust. The presence of such a powerful central engine will have profound implications for the evolution of the supergalaxy. It will regulate the growth of stars and influence the dynamics of gas and dust within the galactic core, potentially triggering quasar-like phenomena as material falls into the black hole and emits intense radiation across the electromagnetic spectrum. On a larger scale, the merger of the Milky Way and Andromeda will contribute to the ongoing evolution of cosmic structure in the universe. Galaxy mergers and interactions are crucial processes in the hierarchical formation model of galaxies, where smaller structures merge to form larger and more complex systems over cosmic time. Studying galactic collisions like the one between the Milky Way and Andromeda provides astronomers with insights into the mechanisms driving galaxy formation and evolution. By observing how stars, gas, and black holes interact during such events, scientists can test theoretical models of galaxy mergers and refine our understanding of the physical processes at play. The merger will also have implications for the distribution of dark matter within the newly formed supergalaxy. Dark matter, an invisible and elusive form of matter that comprises a significant portion of the universe's mass, plays a crucial role in shaping the structure of galaxies and their gravitational interactions. During the merger, the gravitational forces exerted by the dark matter halos surrounding the Milky Way and Andromeda will interact and merge, influencing the overall distribution of dark matter in the new galaxy. Observing the effects of dark matter during and after the merger will provide valuable clues about its nature and properties, helping astronomers unravel one of the biggest mysteries of modern cosmology. The merger between the Milky Way and Andromeda will also provide a unique opportunity to study the formation of galactic clusters and superclusters. These vast cosmic structures, composed of multiple galaxies bound together by gravity, are the largest known structures in the universe and provide insights into the large-scale distribution of matter and the formation of cosmic web-like structures. As the Milky Way and Andromeda merge, they will bring their respective satellite galaxies along for the ride. These smaller galaxies orbiting around their larger counterparts will be gravitationally drawn into the merger process, either merging with the new supergalaxy or being torn apart and assimilated into its extended halo of stars and gas. The fate of these satellite galaxies will depend on their orbits and velocities relative to the merging Milcomda system. Some may survive the merger relatively intact, becoming dwarf galaxies within the new supergalaxy, while others may be disrupted and ultimately assimilated into the larger structure. The merger between the Milky Way and Andromeda will also have implications for the cosmic environment surrounding our solar system. While the collision itself will not pose a direct threat to Earth, the gravitational disturbances and influx of cosmic rays from the merging galaxies could have subtle effects on our planet's climate and micro-ray exposure over geological timescales. Moreover, the formation of the new supergalaxy, Milcomda, will create a fundamentally different night sky for any future inhabitants of the Milky Way. The merger will rearrange the positions and distributions of stars, star clusters, and nebulae, potentially creating new constellations and celestial landmarks that will shape the cultural and navigational aspects of any civilization that arises in the distant future. In conclusion, the collision and merger between the Milky Way and Andromeda represent a cosmic spectacle on an unimaginable scale. It is a process that will transform both galaxies, creating a new supergalaxy that blends the material and characteristics of its progenitors into a unified cosmic entity. From the reshaping of spiral arms and the birth of new star clusters to the coalescence of supermassive black holes and the redistribution of dark matter, every aspect of the merger will leave an indelible mark on the future evolution of the local group of galaxies. Studying this event provides astronomers with a unique opportunity to witness the transformative power of gravitational interactions in shaping the universe we inhabit. It is a reminder of the dynamic and ever-changing nature of cosmic evolution, where galaxies collide, merge, and ultimately give rise to new structures and phenomena that continue to inspire awe and curiosity in the exploration of the cosmos.
Out in the vastness of interstellar space, humanity's farthest messenger continues its journey through the cosmos. Launched in 1977, NASA's Voyager 1 stands as a pinnacle of space exploration. This mission not only revolutionized our understanding of Jupiter, Saturn, and their many moons, but also gave us our first up-close view of the mysterious and awe-inspiring planets Uranus and Neptune, as Voyager 1 has just made contact with an unknown force in deep space. As you watch this video, consider that both Voyager probes are still active, venturing into interstellar space, a realm untouched by any human-made object before. However, amid their trajectory through this uncharted territory, something unsettling is occurring aboard one of NASA's iconic 20th century spacecraft. Eerie signals are being captured from interstellar space. Is Voyager merely encountering an unknown force? Are these signals messages from extraterrestrial beings? And if so, are they friendly greetings or potential threats? These questions have intrigued scientists for decades. Since their launch, Voyager 1 has traveled more than 15 billion miles, while Voyager 2 has surpassed 12 billion miles. Take a moment to reflect on the vision that sparked the creation of Voyager, its monumental achievements, and its lasting legacy. Consider how these two probes and their discoveries have inspired subsequent missions and continue to shape NASA's endeavors today. In quieter moments, think about a distant future, billions of years from now, when our sun evolves into a red giant. By then, Earth will no longer be habitable, and humanity may have sought refuge on another celestial body, following the path blazed by the Voyager missions. It's both humbling and inspiring to imagine that even in that distant era, the Voyagers will remain as Earth's ambassadors, serving as time capsules from an age when intrepid explorers from our pale blue dot reached out to the stars. Beyond the scientific contributions of the Voyager mission, the probes themselves have captured the world's imagination by carrying greetings for potential extraterrestrial civilizations in the form of golden records. While Pioneers 10 and 11 carried simple metal plaques, Voyager's golden records were far more ambitious, containing images and sounds that offer a snapshot of Earth's diverse life and culture to any potential discoverers. The Voyager mission stands out as one of NASA's most ambitious endeavors, collectively visiting more planets, discovering more moons, and capturing more images than any other spacecraft in NASA's history. Why were there two Voyagers? In the early days of NASA, flight systems often encountered anomalies that required them to enter safe mode, shutting down instruments until further commands could be received. Given the flyby nature of the Voyager missions, such anomalies could lead to missed encounters and lost scientific opportunities. Thus, having two spacecraft increased the mission's chances of success, a strategy later mirrored in the Mars exploration rovers Spirit and Opportunity. Reflecting on their grand tours of the solar system, the Voyagers provided invaluable insights through tens of thousands of images and measurements, fundamentally altering our comprehension of the outer planets. For instance, at Jupiter, they provided the first detailed insights into the planet's atmospheric dynamics, revealing the counterclockwise rotation of the Great Red Spot and its interactions with smaller storms. The Voyager missions marked significant milestones in space exploration, particularly with their groundbreaking observations of the outer planets. Notably, they were the first missions to detect a faint dusty ring around Jupiter. At Jupiter's moon Io, they revealed volcanic activity. Additionally, the linear features on Europa hinted at a potential subsurface ocean, and Ganymede was found to be the largest moon in the solar system. As the spacecraft journeyed past Saturn, they examined the composition and structure of its atmosphere. Voyager 1's observations of Titan's thick haze led to the hypothesis of liquid hydrocarbons on its surface, a notion later confirmed by subsequent missions. The probes also identified gaps and waves within Saturn's rings, while Voyager 1 discovered 3 previously unknown moons: Atlas, Prometheus, and Pandora. Voyager 1 continued its journey beyond the solar system, while Voyager 2 ventured toward Uranus. At Uranus, Voyager 2 uncovered 11 new moons and 2 previously undiscovered rings. Yet certain phenomena, such as Uranus's peculiar magnetic field and the consistent temperature across latitudes, remained puzzling. Voyager 2's final destination, Neptune, revealed 6 new moons and rings, studied Neptune's composition and magnetic field, and even identified volcanic vents on its massive moon Triton. Ultimately, both Voyagers embarked on a trajectory into interstellar space, where they breached the heliopause, the boundary where the solar wind yields to the pressure of the interstellar medium. Voyager 1 officially entered interstellar space in August 2012, a discovery confirmed by analyzing electron oscillations during a solar eruption. This revelation contradicted expectations, as interstellar space exhibited higher electron density than just inside the heliosphere. The departure date was pinpointed through electron oscillations and a significant drop in solar particles on August 25, 2012, the day Neil Armstrong passed away. At this point, Voyager 1 was 11.5 billion miles from the Sun. Interstellar space, the vast expanse between stars, is not devoid of matter. Approximately 70% of it consists of hydrogen, with helium making up about 28%, both originating from the Big Bang. The remaining 2% comprises heavier gases and dust formed within stars and released into space by supernovae. Despite its sparse nature, the interstellar medium is crucial, serving as the birthplace of stars. The presence of thick and thin regions in this medium, known as molecular clouds or stellar nurseries, is essential for star formation. Initially, the universe consisted of simple elements like hydrogen and helium. However, as stars aged and underwent supernova explosions, they released more complex elements into interstellar space. This process allowed for the formation of stars with planets. A shift from the early universe when planets did not exist, molecular clouds are vital in this process, acting as the breeding grounds for new stars. The evolving elements in stars' interiors contribute to the increasing complexity of materials in interstellar space, leading to planets like Earth, which have the potential to support life. The Voyager's venture beyond the heliopause marked a historic moment. They became the first human-made objects to explore uncharted territory where no spacecraft had gone before. Scientists anticipated groundbreaking insights into space exploration and the fundamental question that has fascinated humanity for centuries. Are we alone in the universe? As we delve into the cosmos, the discovery of exoplanets, particularly those Earth-sized and inhabitable zones, has intensified the search for extraterrestrial life. The Drake equation, though filled with many unknowns, offers hope for determining the existence of intelligent civilizations. Despite the immense potential for life in the universe, the apparent silence, known as the Fermi paradox, raises questions about why we have yet to encounter extraterrestrial intelligence. Voyager 1's journey into interstellar space has yielded valuable data, revealing intense cosmic radiation and illustrating the interaction between charged particles from the Sun and those emitted by other stars. Despite its age, the spacecraft continues to astonish engineers. In December 2017, Voyager 1 successfully employed its backup thrusters, unused since 1980, showcasing its resilience and potential for extended operational life. As we stand at the crossroads of the search for life beyond Earth, our increasing technological capabilities offer hope that we may one day find answers to the mysteries of the cosmos. The Allen Telescope Array in California recently achieved an extraordinary feat by detecting a signal from NASA's Voyager 1 probe, launched 46 years ago and now hurtling toward the outer edges of our solar system, well beyond Pluto. The observatory, dedicated to the search for extraterrestrial life, used 20 of its 42 dish antennas, each over 61 meters wide, to contact Voyager 1. The telescope recorded 15 minutes of data stored on a disk, but the nature of the signal remains undisclosed. Speculations about the signal range from encounters with mysterious forces in space to the unsettling notion of aliens hijacking Voyager 1. Some even suggest that these signals are messages from higher civilizations to humanity, leaving the nature of the messages uncertain, whether they bring a friendly greeting or pose a potential threat. Voyager 1, now about 151 billion kilometers away from Earth, is still being tracked by NASA's Deep Space Network. Its data transmission rate remains modest at 160 bits per second. Despite this limited transfer speed, the probe, powered by a device that converts plutonium's radioactive decay into electricity, has provided invaluable information. However, with its power output decreasing by about 4 watts annually, NASA faces challenges in keeping Voyager 1 operational. Triage measures have been implemented, including turning off the cosmic ray detector's heater, once essential for determining heliopause transit. Although the last 2 instruments may persist for a few more years, the declining power output is a critical factor. Looking ahead, the Voyagers may only last a few more years, perhaps into the 2030s if everything goes well. Yet even after their instruments fall silent, these spacecraft will continue their interstellar journeys. In approximately 16,700 years, Voyager 1 will pass Proxima Centauri, our nearest neighboring star, followed by Voyager 2 about 36,000 years later. Both will continue to orbit the galaxy for millions of years, outlasting the sun's collapse and the demise of the heliosphere. These iconic spacecraft may, during their travels, convey a final message encoded on golden records made of copper coated with gold and sealed in aluminum covers. These records contain images, sounds, and messages designed to give a sense of Earth. Although they were meant to last for perhaps 1 billion years, their actual survival depends on external conditions, with dust grains in space posing a potential threat. Dust particles could slowly erode the spacecraft's surfaces over time, presenting a challenge for the long-term preservation of the Voyager mission's artifacts. There is also the possibility that the gravity of interstellar clouds could affect the Voyager's trajectories. These massive clouds, concentrated with substantial mass and gravitational forces, could alter the direction of the spacecraft, depending on the density of the medium they traverse. Additionally, micrometeorites, small particles moving at velocities up to 50 kilometers per second, could damage the Voyagers. Given the billions of years ahead, the spacecraft are likely to sustain some impacts. Despite these challenges, Voyager's achievements remain extraordinary. Originally intended to last 5 years, they have persisted far beyond expectations. Their longevity attests to the brilliance of their design, extending their missions for decades. Over the next few years, both spacecraft will continue.
As the James Webb Telescope brought us a little closer to God, the telescope's new discoveries are shocking all religious people. We are facing a paradigm shift that challenges not only our science, but also religious ideas about the universe. James Webb Telescope's terrifying new discovery shocks all religious people. The last time there was such a revolution was when Galileo Galilei found out that the Earth is not the center of creation, and when science realized 100 years ago that the Milky Way is not the universe. The James Webb Space Telescope is one of the most impressive scientific instruments we humans have ever created. With its ability to peer deep into the universe and gather light from the earliest stars and galaxies, this telescope is far more than just a technical instrument. It's a symbol of mankind's search for truth. Galileo Galilei said, "Nature is a relentless judge who forces us to strive for knowledge." Many people believe that we can only understand the inexorable nature if we have found God at the same time. Perhaps it was God Himself who put the spirit of inquiry in us to discover the secrets of the universe, and perhaps him or her. We do not know what God really is, and whether this entity really exists. Science is not just for our curiosity or our fear of a nature we cannot control, and a universe so gigantic that we feel like nothing in it. Science should also provide us with answers to the deepest questions of our existence. Even though the JWST and the entire scientific mission of humans can be seen as divine in this context, there are religious currents that vehemently reject all new knowledge and science. The JWST has made such shocking discoveries that even science is currently amazed. It has observed some of the oldest known galaxies, more than 13.7 billion years old, and has provided evidence for the existence of water in the atmospheres of exoplanets. These discoveries could take our understanding of how the universe formed, and how life exists in it to a whole new level. If the JWST finds the first evidence of life on other planets, then we must realize, whether religious or not, that God did not create just one world but many. One particularly fascinating aspect that is now coming into focus more than ever before is the multiverse, previously dismissed as nonsense by conservative science. The latest shocking discoveries make it increasingly likely that multiple universes exist. Fascinatingly, the world's three major religions do not recognize this idea, and even oppose it. But in Asia, it's quite different. The Vedas describe the existence of many worlds inhabited by gods, demons, and other beings. We don't have to go that far to find the idea of the multiverse in religion. The Germanic mythology of 9 different worlds created by the gods is nothing other than a multiverse. Such parallels could indicate that the scientific discoveries of JWST have a deeper spiritual dimension, and that we are on the verge of reuniting religion and science. In ancient times, this was quite normal. The two disciplines were inseparable. Mathematics, music, mechanics, everything was considered divine, and therefore also religious. The reasons why church leaders and other religious rulers rebelled against modern astronomical discoveries must therefore be of a different nature. Galileo Galilei versus the Church. Who doesn't know the name Galileo Galilei today? The great mathematician and astronomer lived in Italy from 1564 to 1642. What hardly anyone knows today, however, are the problems Galileo had to contend with. Galileo was the first to improve the telescope, and the resulting astronomical observations led him to the heliocentric view of the world. The scientist discovered the 4 largest moons of Jupiter, the phases of Venus, sunspots, and the uneven surface of the moon, which provided evidence for the heliocentric model. Galileo lived during the Renaissance, a time of intellectual and cultural change in Europe. This era was characterized by great advance in art, science, and literature. But at the same time, there was still strong religious control by the Catholic Church, especially in the early days of this era. The Church had no interest in reviving the old scientific worldview of antiquity, and saw the teachings of the ancient sages as a threat to its power and world order. This included, for example, the advocacy of the geocentric view of the world, which was based on the teachings of the ancient astronomer Claudius Ptolemy and the writings of the Bible. This model placed the Earth at the center of the universe, and was seen as the only true divinely ordered structure. When Galileo publicly advocated the heliocentric model, he got himself into a lot of trouble with the Church. The Inquisition was something of a counter-term movement to the Renaissance. All modern ways of thinking and naturopathy and disciplines such as astrology, which were still highly valued in ancient times, were to be destroyed. In 1616, the Inquisition declared the heliocentric view of the world, first postulated by Nicholas Copernicus, to be heretical. Galileo was brought before a church court in 1633, convicted of heresy, and forced to recant his views. The scientist was allowed to live, but he spent the rest of his life under house arrest. The Church's rigid attitude towards the heliocentric model was officially due to the fact that the Bible portrays the earth and humanity as the center of God's creation. Any challenge to this worldview was seen as a threat to this authority and the divine order or the power of the Church. If it had become public that the Church had distorted itself, this would have diminished the power of the Church. Giordano Bruno, another Italian scientist, was hit even harder. He was once even a priest, but also loved astronomy. Bruno went a step further than Galileo. He postulated the infinity of the universe and the existence of countless inhabited worlds. These ideas could have been visionary, but for Bruno, his genius ended at the stake. The Church regarded Bruno's ideas as extremely dangerous and gave him a lengthy trial to deter other researchers. Bruno died a completely senseless death as a heretic in 1600. The Church only apologized for these crimes in modern times, but did you know that the Catholic Church has never really recognized the modern findings of science? Big Bang versus creation story. One of the lesser-known facts today is that it was a priest who came up with the Big Bang theory. For the Belgian Georges Lemaitre, religion and science were not contradictions. He said, while science deals with the how of the universe, religion explains the why. Lemaitre held the view that scientific discoveries and religious beliefs can coexist harmoniously as long as they focus on their respective areas. The then Pope Pius XII first commented on the Big Bang theory in 1951, saying in a brief statement that the Big Bang could also be seen as a divine act of creation. Nevertheless, it naturally became clear that the stories of the Bible could not be truths, but merely allegories. God certainly did not create the earth in a week. Incidentally, Islam also has an almost identical creation story. Allah created the earth in 6 days, and there was a man and a woman who resemble Adam and Eve. Let's take a closer look at the idea of the Christian, Islamic, and Jewish creation stories. The apparent accuracy of the ideas reflected in the respective Holy Scriptures is astonishing. 6 days of creation and man was there first. And of course, the man who is right and can command everything, the animals and the earth, belong to man. Now let's look at the scientific findings. The Big Bang was an event that lasted less than a second, and a measly 9 billion years passed before the earth appeared. Maybe that's really no more than a week in God's kingdom, but we need a lot of imagination then. We know today that we humans were not there first either, but the plants and animals were. That doesn't quite fit in with many church people either, and certainly not with the realization that humans were once animals, and still are to some extent. Today, a new revolution in worldview is imminent. Is the earth flat or round? Is it the center of the universe or just one part of countless others? Is the universe finite or infinite? And above all, are there several universes? Even those who are not religious are influenced by such new findings on a metaphysical level. An infinite universe would mean that our science has so far understood absolutely nothing, and that the universe challenges our human understanding. There are Buddhist monks and believers in Asia for whom the idea of infinity is not a spiritual problem. They even claim to be able to see the infinity of the universe with the third eye. It's only our Western science and us normal people who have a very narrow view of the world due to our school education. We also believe that only one or the other can be true, whereas quantum mechanics, for example, shows us that there can be countless variations of reality side by side. If the James Webb Telescope now proves the Big Bang never happened and that the universe is infinite, this will blow up the old science, and that is probably a good thing because we are no longer getting anywhere. The JWST is currently driving our science up the wall on several levels, and the researchers are resigning themselves. Our knowledge and our methods can no longer describe the universe as it now appears. What does this mean? a return to metaphysics, or is the long overdue unification of quantum physics and classical physics about to happen? In quantum mechanics, scientists are researching particles that carry all the information in the universe, and that can be in several places and at several times at the same time. Quanta are the basic building blocks of matter. If these particles have such properties, we have to reckon with the fact that the world of matter is not what we think it is. It could be an illusion, a changeable projection, and there is even evidence that we ourselves create this world. Would that then mean that we ourselves are God? Possibly. There are certainly views and even scientific theories that God is everything we can see, an infinite consciousness, and an intelligence that is beyond our normal mental comprehension. But if this is the case, and God is in each of us, then we should still be able to discover Him and the blueprint. The Webb telescope looks so far out that it's capturing light that's been traveling for over 13 billion years. However, the universe has been expanding, causing the light to stretch. For the most distant galaxies, we're looking back in time almost to the Big Bang. The Big Bang stands as a definitive narrative of modern cosmology, boldly asserting that our universe had a beginning and possesses a finite age. However, the concept of a singular cosmic beginning, followed by billions of years of cosmic expansion, has faced skepticism since its inception, and doubters have challenged its validity within mainstream cosmology. Cosmic Journey. Brian Cox, James Webb. Insane discovery could destroy the universe. Doubts about the Big Bang largely dissipated in the 1960s with the discovery of the cosmic microwave background, a pervasive radiation buzz that aligns coherently as a remnant from the universe's early hot era. Nevertheless, doubts have persisted over time and gained traction recently due to groundbreaking revelations from the James Webb Space Telescope. In a stunning observation, NASA's time machine, the JWST, which has the capability of detecting 13-billion-year-old light, as explained by the famous British physicist Brian Cox, identified an inconceivable mass of galaxies at the edge of the observable universe. This discovery has challenged the validity of the Big Bang theory. Now the question is, could it be time to reshape our understanding of the cosmos and our existence entirely? Let's dive in to find out. The Hubble telescope was not sensitive enough to detect that light, but the Webb can see the formation of the first galaxies. It's essentially looking all the way back to very close to the beginning of time, and that's crucial because we're not entirely sure how those first galaxies formed. We can see that it's microwaves because the light has been stretched so much by the expansion of the universe. The problem with light is that in those earliest times, the universe was so hot and dense that light couldn't travel through it, making it opaque. So you can't use light to go back earlier than that. However, with the technology we have now to detect colliding black holes, we might one day probe right back to the Big Bang and determine whether or not that's the origin of time. The concept of the Big Bang traces back to the 1920s and 1930s, when observations of distant galaxies revealed a peculiar pattern. The farther away they were, the faster they seemed to recede. Following Albert Einstein's general relativity predictions, a static universe would be gravitationally unstable, necessitating either a divergence or a collapse if space adhered to his laws. The observation of the apparent recession taught us that the universe is presently expanding, implying that things were closer together in the distant past. The expansion of the universe not only signifies increasing distances over time, but also entails the stretching of light wavelengths as we progress through time. Since wavelength corresponds to energy, with shorter wavelengths being more energetic, the universe cools as it ages, indicating hotter conditions in the past. If we trace this expansion back far enough, we reach a point where everything was so hot that neutral atoms couldn't form. According to this scenario, we should detect a residual radiation glow today in all directions, having cooled to just a few degrees above absolute zero. The groundbreaking discovery of this cosmic microwave background in 1964 by Arno Penzias and Bob Wilson served as a stunning confirmation of the Big Bang. The temptation lies in continuing this exploration backward in time to an era when the universe was even hotter, denser, and more compact. It's really the light from the origin of the universe. If you have an old FM receiver and you tune between channels without capturing a station, you'll hear noise. If you have a good radio set, 1/2 of 1% of that noise is actually the sound of the Big Bang. As we trace back in time, we encounter a period when it was too hot for atomic nuclei to form, causing radiation so intense that it could break apart any bound protons and neutrons. During this energetic phase, matter and antimatter pairs could spontaneously emerge. Further back, protons and neutrons disintegrate into a quark-gluon plasma, where the universe reaches densities surpassing those inside an atomic nucleus. Ultimately, the density and temperature reach infinite values, representing a singularity where all matter and energy converge into a single point, signifying the breakdown of the laws of physics. This singularity not only marks the point where the laws of physics falter, but is also perceived as the origin of space and time, encapsulated in the fundamental concept of the Big Bang. Every aspect of this journey except for the final singularity has been substantiated. Quark-gluon plasma has been synthesized in laboratories, matter-antimatter pairs have been created, and calculations aligning with the Big Bang's predictions have been confirmed through measurements of early universe elements and their abundances. Moving forward, observations have extended to measuring fluctuations in the cosmic microwave background, providing insights into the formation and growth of gravitationally bound structures like stars and galaxies. While the Big Bang theory demonstrates remarkable agreement between theory and observation, the universe as we perceive it presents certain features and enigmas that the Big Bang alone doesn't entirely elucidate. If everything originated from a singular point within a finite timeframe, one would anticipate varied temperatures in different regions of space, as these regions wouldn't have had the chance to interact and exchange particles, radiation, or information. Moreover, remnants from the earliest hottest periods, such as magnetic monopoles and topological defects, and some degree of spatial curvature, should exist. Since a singularity-originated Big Bang lacks a mechanism to balance the initial expansion rate with total matter and energy density, contrary to these expectations, the universe maintains a uniform temperature across all regions, lacks high-energy relics, and exhibits perfect spatial flatness in every direction. This leads to two possibilities. Either the universe inexplicably possessed these properties from its inception, or there exists a scientific explanation, a mechanism that orchestrated the universe's emergence with these specific properties. On December 7, 1979, physicist Alan Guth had a groundbreaking realization suggesting an early period of exponential expansion preceding the Big Bang. The phenomenon we now recognize as cosmic inflation could account for the universe being endowed with these specific properties from the outset. The end of inflation would then mark the transition, giving rise to the subsequent hot Big Bang. In the realm of science, one cannot simply introduce an additional idea into an existing theory and claim superiority over the new one. The burden of proof for a new theory is notably stringent. Persistent doubts surrounding established theories have recently heightened, fueled by groundbreaking revelations from the James Webb Space Telescope exploring the early universe. In its inaugural year of scientific operations, the $1 billion infrared telescope has provided breathtaking glimpses of the nascent universe, unveiling surprisingly bright galaxies from a time when the cosmos was in its infancy. With its 6.5-meter mirror, the JWST was specifically crafted to investigate this early era, a domain mostly beyond the reach of its predecessor, the 2.4-meter Hubble Space Telescope. The JWST's observations have left researchers astounded, grappling with the implications of their findings. According to the Standard Model of Cosmology, following the fiery Big Bang around 13.8 billion years ago, the universe underwent cooling, and energy transformed into matter over the first few 100 million years. This matter coalesced, giving rise to the first generation of stars and galaxies. While astronomers believed they had a solid grasp of this process, the JWST's preliminary outcomes suggest that stars and galaxies might have formed at a much more accelerated pace than previously envisioned. Headlines have even proclaimed that the telescope has essentially broken the universe and overturned models of cosmic history. However, following subsequent data analysis from the JWST, some of the initial striking findings have been dismissed, and new simulations can now accommodate a few of the peculiar observations. Certain bright, massive, and early galaxies persist in challenging theorists, implying that our comprehension may undergo shifts in the years to come. Priyamvada Natarajan, a theoretical astrophysicist at Yale University, emphasizes that current data hasn't broken the universe, but intriguing potential tensions are emerging on different scales. Resolving these tensions will necessitate researchers reassessing their foundational assumptions about galactic evolution, potentially introducing new ideas while relegating others to the cosmic dustbin. It's noteworthy that the discovery of these early galaxies is not a recent occurrence. In May 2009, astronauts installed one of Hubble's crucial instruments, the Wide Field Camera 3, WFC3, vastly enhancing the telescope's infrared vision. As the universe expands, light traveling through space gets stretched into longer wavelengths, or the redder portions of the electromagnetic spectrum. The oldest entities therefore become visible in the infrared, beyond the reach of shorter ultraviolet or visible wavelengths. WFC3 empowered Hubble to capture light from remarkable objects, including the galaxy GNZ11, which existed when our universe was a mere 3% of its current age, or approximately 400 million years old. However, Hubble faced limitations in exploring this early epoch, with few visible big, bright galaxies due to constraints in its instruments, hindering astronomers from witnessing the very beginnings of galaxy formation. Upon the JWST launch in December 2021, scientists rapidly dismissed the initial possibility of no galaxies existing within the first 500 million years after the Big Bang. The discovery of the galaxy class Z12, approximately 50 million years older than GNZ11, and subsequent JWST observations revealing numerous galaxies potentially as early as 180 million years after the Big Bang, refuted the earlier notion. J.N. Cardultep, an astrophysicist at the Rochester Institute of Technology, notes the surprise among researchers at the abundance of bright galaxies detected with the JWST and their unexpected ease of identification. Additionally, these galaxies may be more massive than previously theorized. In the initial period after the Big Bang, intense conditions prevented the settling and condensation of matter into entities like stars and galaxies. Radiation generated by matter-particle collisions was in equilibrium with the rate of particle creation and destruction. Consequently, the radiation pressure hindered gravity's ability to initiate the collapse of the first stars. For an extended duration, the cosmos remained a glowing soup of hot particles, experiencing gradual cooling over time. As this process unfolded, atoms began to form as nuclei captured electrons. The formation of neutral hydrogen atoms allowed the light to traverse the universe, setting the stage for gravity to foster the formation of the earliest stars and galaxies. When the first stars ignited, they initiated a new era known as the epoch of reionization, marking the universe's second phase transition. Radiation emitted by early stars and galaxies reionized the neutral atoms, restoring the universe to its ionized state. It is during this transition from neutral to ionized atoms that these bright early galaxies likely emerged. The timeline for the formation of the earliest galaxies remains uncertain, but researchers are certain that it occurred rapidly, possibly within a few 100 million years following the Big Bang. Theorists are currently grappling with the implications of the JWST's findings, as the early galaxies appear surprisingly luminous, dense, and massive compared to expectations. If such massive galaxies indeed existed during the epoch of reionization, this could suggest that star formation processes were more efficient than previously assumed, possibly indicating an overestimation of the time required for stellar birth. Richard Ellis, an astronomer at University College London, highlights the puzzling nature of these observations, as larger galaxies should experience gravitational interactions that disrupt star formation, leading to dimmer systems. Additionally, galaxies appear to have formed in abundance, surpassing predictions from cosmological models. Galaxies like these would have required rapid, almost flawless assembly, forming vast numbers of stars in a short time frame, while competing with intense radiative feedback that would impede further star formation. Numerous avenues could explain the emergence of these galaxies. One possibility is that the earliest galaxies primarily hosted massive, short-lived stars known as population 3 stars, distinct from the stars observed today. Such stars would quickly exhaust their nuclear fuel and explode as supernova, seeding their host galaxies with heavier elements, a process that would foster even more efficient star formation. Another potential factor is the existence of black holes within galaxies, which could fuel bursts of rapid growth in these early systems. However, challenges remain in verifying these ideas, particularly given the high mass estimates for these early galaxies, which pose theoretical difficulties. One of the most pressing challenges for astronomers is reconciling the JWST's discoveries with existing cosmological models. While these models have successfully described the large-scale structure of the universe in the cosmic microwave background, the early galaxies observed by the JWST might require adjustments to our understanding of galaxy formation and evolution. Some astronomers argue that the discrepancies between the JWST's findings and current models may necessitate a re-evaluation of the parameters used in these models. For example, researchers may need to reconsider the role of dark matter in the early universe or explore alternative explanations for the rapid formation of massive galaxies. As researchers continue to analyze the JWST's data and refine their models, the possibility remains that our understanding of the early universe could undergo a significant transformation. However, It's also possible that the discrepancies will be resolved without requiring a complete overhaul of current cosmological theories. For now, the JWST's discoveries have injected a sense of excitement and curiosity into the field of astronomy, prompting scientists to explore new ideas and rethink old assumptions about the universe's origins. The James Webb Space Telescope is the first step in answering some of the deepest questions about our existence. What are we? Where did we come?
There is something wrong with the universe, and nobody really knows what it means at the moment. The James Webb Telescope has discovered galaxies that theoretically existed before the Big Bang. This challenges the Big Bang theory and our entire cosmology to date. Science now faces a seemingly unsolvable problem. Although researchers like the Swiss Fritz Zwicky proposed alternative explanations for our universe 100 years ago, these theories are now becoming relevant again. Something is wrong with the universe, James Webb Telescope, and the galaxies before the Big Bang. Hardly any schoolchildren today know the name Fritz Zwicky, but names like Albert Einstein, George Lemaitre, and Edwin Hubble are well known. These researchers laid the foundation of our cosmology for almost 100 years. Albert Einstein described space-time, Lemaitre proposed the Big Bang, and Hubble observed the apparent expansion of the universe. But now, all these theories are being put to the test, and the new superstar among telescopes is responsible for this, the James Webb Space Telescope. This marvel of technology has provided us with many fascinating images of a previously unknown universe, revealing that the old theories might be wrong or at least incomplete. Fritz Zwicky was a contemporary of these great researchers. The Swiss physicist, who also studied the movement of galaxies and the dynamics of the cosmos, proposed a theory that is once again topical and the subject of heated debate today. The idea of tired light is very simple. Zwicky postulated that light is not constant, as Einstein claimed, but that it undergoes a physical change during its journey through time and space, which he called fatigue. Einstein asserted that nothing travels faster than light, and that the speed of light is always constant, not relative like other known forces in the universe. It seems logical that researchers have long used light and its speed as benchmarks for exploring the universe and determining important values such as distances and the rate of expansion. Before we examine the potential flaws in these theories, let's explore some of the fascinating galaxies discovered by the Webb telescope, galaxies that should be impossible. With its ultrafine sensors, the Webb telescope looks further back in time than any previous telescope. Thanks to red light spectrography, Webb can detect light that is very faint and highly redshifted. The first deep image of the universe showed galaxies that existed an estimated 13.6 billion years ago. The remarkable thing is that no galaxies were supposed to exist at that time. It all began with the astonishing discovery by Harvard student Rohan Naidu. He and his team announced the discovery of Glass Z13, a galaxy that demonstrably existed around 200 million years after the presumed Big Bang. Its age suggested, at the beginning of the Webb era, that galaxies could have evolved faster and earlier than previously thought. However, some researchers were initially skeptical. Then came GN Z11, and with an estimated age of 13.4 billion years, this galaxy once again provided overwhelming proof that the old theories might no longer hold. GN-Z11 is one of the most distant known objects in the universe, originally discovered by the Hubble Space Telescope. The discovery was only confirmed by the Webb telescope. GN-Z11 offers insights into early star formation and galaxy formation in the young universe. Thanks to Webb's stunningly accurate spectrometer analyses, it is now clear that stars and fully formed galaxies existed much earlier than previously known. Sears 9316 was discovered by the Cosmic Evolution Early Release Science Survey. This galaxy was originally estimated to be an incredible 13.8 billion years old, sparking enthusiasm among some researchers and challenging others. The other galaxies still allowed for the idea of a much faster evolution of matter. This was the loophole for researchers eager to hold on to the Big Bang theory. However, a galaxy as old as the Big Bang itself challenges this view and makes new approaches, such as the eternal universe or Zwicky's theory of tired light, more plausible. The age of Sears 93316 is still the subject of heated debate, with the discoverers constantly presenting new evidence for the authenticity of the find, while critics attempt to refute this evidence. HD1 is another unusual galaxy with an estimated age of 13.5 billion years. It is one of the most luminous galaxies among the very old galaxies discovered so far, indicating an unusually high rate of star formation. These are the facts that scientists are searching for, as HD1 could help us significantly deepen our understanding of the conditions and processes in the universe during this epoch. Let's take another look at MAX 0647-JD. It's not one of the lesser-known newly discovered galaxies, but it still has some interesting features. MAX 0647-JD was discovered by gravitational lensing with the Hubble Space Telescope and then further studied with the Webb telescope. With an estimated age of 13.3 billion years, MAX 0647-JD is not one of the oldest galaxies, but strangely, it is one of the most evolved. It existed only 500 million years after the Big Bang, but shows such a high degree of order and size that it should actually be several billion years old. This suggests that the formation time of this galaxy would have been before the Big Bang, which defies current understanding. These galaxies are only 5 of the 15 confirmed impossible galaxies, and there are more to come. Tired light, Zwicky already knew about it 100 years ago. Imagine, the most crucial component that scientists have used to study the universe has been misunderstood until now. Light is not constant, but becomes tired over time. Minimal differences are enough to change distances of several million light years, rendering our measurements completely wrong. Another possibility within this theory is that light physically behaved completely differently 13 billion years ago. Consider this. The light that now hits the observation mirrors of the Webb telescope was emitted 13 billion years ago or more by stars that no longer exist. Of course, the Earth did not exist at that time, not even our Sun. And it's very likely that only a small precursor of our galaxy existed. These particles of light, therefore, traveled incredibly far and for an incredibly long time. As the light traveled, space also expanded. If the idea of the expansion of the universe is true, this expansion could have stretched the light, but we don't know that for sure. We have no way of measuring or investigating the original light. We can only deal with the light that has undergone this extremely long journey. We also cannot travel back to the time when the light was created. Despite these hurdles, these faint light signals are actually miraculous. The mysteries of time and space and the journey of light allow us today to study the universe as it was 13.5 billion years ago. This is fantastic. Interpreting the signals is really a bit of a guessing game. Researchers have to take all the fixed known quantities and then derive constants, similarities, and meanings. This is how our theories and explanations are created. In addition to light, there are several other quantities that researchers use to measure and describe space. These are certain phenomena that always behave in a consistent way. If it turns out that this was precisely the mistake, we really are facing a complete reorientation of science. Rendra Gupta is a Canadian researcher who, in 2023, put forward a theory showing that a small modification of these cosmic constants quickly leads to a much older universe. But not only the age of the cosmos would then change, variables relating to expansion and origin could also be completely different. Gupta presented a coherent calculation according to which the universe could be 26.7 billion years old. However, he also showed that a further small adjustment would lead to an age of 40 billion years. This would explain why we see masses of galaxies in Webb's images that suggest a much older universe. Gupta also considers Zwicky's ideas and shows that the picture of our universe turns 180 degrees when just this one small component of tired light is taken into account. Science can go no further. It is fascinating to observe how the world of science reacts to the new circumstances. One person who was excited about the new findings is U.S. astronomer and astrophysicist Michio Kaku. Kaku is regarded as an exceptional researcher who has written many books to bring the mystery of the universe closer to ordinary people. He enthusiastically explained that the Webb telescope completely reshuffles the cards in science, and Kaku welcomes the changes. He knew for a long time that something couldn't be right. Kaku, in addition to his passion for the visible universe, is a big proponent of quantum physics. Quantum physics and classical physics still don't really go hand in hand, which proves once again that we must have a flaw in the system. Other researchers, such as a third scientific genius whose name is currently being discussed a lot in the press, is Sir Roger Penrose. A few years ago, the scientist from Great Britain postulated a cyclical universe in which there is a kind of basic matrix that transports the idea of matter from an old universe into a new one. According to this, all information is stored when an old universe dies, and in this way, matter could be quasi-turbo recycled in a new universe, which could lead to a faster formation of stars and galaxies. Penrose's model also predicts that black holes play a crucial role in these cycles. In his model, they are pretty much the last objects or physical entities left at the end of a universe. Penrose, who is already a Nobel Prize winner, could indeed be right in his ideas. But there is one big problem with all these theories. Until the end, they remain theories. We cannot yet look back to the Big Bang or beyond. As fascinating as the new Webb images are, we will always be confronted with a great unknown when we look at the pictures. These are the phenomena that we simply cannot explain, the missing links between the pixels of the images. Light may not be constant, the universe may be much older than we thought, and Penrose's ideas may even be correct, but the whole truth will remain hidden from us. This brings us back to Michio Kaku. His theory about the multiverse could explain how such an impossible universe could exist. A glitch in the matrix or a quantum leap in space could create the illusion of another universe that, in reality, does not exist at all. This, in turn, could solve the problem with the impossible galaxies. Or we are simply wrong, and we cannot interpret the Webb data correctly because of incorrect assumptions. Until science figures this out, we are faced with the eternal question: how do you see the world? Does it end at the edge of the observable universe? Or is there something far beyond that we have no idea about? Are we just a drop in the ocean, or do we occupy a much more important place in the universe than we can imagine? One thing is for sure. If light is not constant and the universe is significantly older than previously thought, then we have to throw almost everything overboard that we have learned so far. This doesn't mean we will stop investigating, but we will always have to keep one thing in mind. Nothing is as it seems.
The James Webb Space Telescope has just achieved a historic milestone by capturing the first ever real and authentic image of Oumuamua. Although this enigmatic interstellar object was first discovered by scientists in 2017, there were a lot of doubts about whether the picture obtained at that time was enough to tell us everything we ought to know about this strange visitor. But now a significant breakthrough has offered new insights with an exclusive image captured by JWST. How relevant is this discovery to scientists, and what new details does it reveal? James Webb Telescope just captured a terrifying object in space. Oumuamua is the first confirmed object from another star to visit our solar system. This interstellar visitor looks like a rocky, cigar-shaped object with a reddish tint. The discoverers named it Oumuamua, which means a messenger from afar arriving first in Hawaii. Oumuamua is up to 1/4 mile, 400 meters, long and very elongated, about 10 times longer than it is wide. This aspect ratio is greater than any asteroid or comet observed in our solar system so far. While its stretched-out shape is surprising and different from objects in our solar system, it could offer new insights into how other solar systems form. The observations suggest that this unusual object has been drifting through the Milky Way, not bound to any star system, for hundreds of millions of years before its unexpected encounter with our solar system. But how exactly was Oumuamua found? Stay tuned, because the most shocking part is yet to come. On October 19, 2017, a strange object named Oumuamua was detected speeding through our solar system. This asteroid had been traveling for over a century before it was finally identified. It reached a significant cosmic milestone in 1837, but astronomers missed it. Oumuamua continued its journey through our solar system for several decades at a steady speed, and astronomers and telescopes failed to detect it. It wasn't until 2017 that Robert Warwick, a scientist at the University of Hawaii, noticed a faint, elongated streak in the sky captured by the Pan-STARRS 1 telescope, revealing a fast-moving object unlike any seen before. Initially, scientists thought Oumuamua was a comet because of its unusual behavior, but they later identified it as an asteroid, a small rocky object usually found in the asteroid belt between Mars and Jupiter. However, further observations showed that Oumuamua was moving away from the sun. Mystery. The lack of visible outgassing, which typically occurs in comets, puzzled scientists as the object accelerated in a way that defied predictions, leading them to question whether it was truly an asteroid or a comet. One of the most remarkable features of Oumuamua was its consistent brightening and dimming every 7.3 hours, indicating that it was tumbling and most likely spinning around its shorter axis. Such speed suggested that Oumuamua was a solid object with a stronger and more durable composition than most comets, which are typically loose and fragile. Its dark red color, similar to that of moons in the outer solar system, showed that it had been exposed to cosmic radiation for millions of years, altering its surface. As experts analyzed the data, suspicions about the true nature of Oumuamua began to surface. Some speculated that it might be an advanced extraterrestrial probe or a defunct alien spacecraft, while others considered more likely possibilities, such as a previously unknown type of comet or asteroid. Even more conservative theories suggest that Oumuamua is a remnant of an exoplanet that was ejected during a catastrophic event in another star system. There is still no consensus on what Oumuamua actually is. Predicting Oumuamua's future path has proven difficult because it has already started to move away from the sun, exiting our solar system at a sharp angle. Current estimates suggest that Oumuamua is returning to interstellar space, where it will continue its lonely journey across the universe. The discovery of Oumuamua sparked intense debate and interest among astronomers, scientists, and the general public. This unusual cosmic object, the first of its kind ever found, inspired a flood of theories trying to explain its origins and nature. Was it just a regular cosmic object, or could it have been an alien probe sent to explore our solar system? Let's look deeper into the various theories and evidence that have emerged in the effort to understand the mystery of Oumuamua. Because of the various data that was gathered, theories concerning Oumuamua evolved. Some experts suggested that Oumuamua might be filled with gas, which could explain its sudden acceleration as it moved away from the sun. Then came the shocking suggestion that it might not be a natural object at all, but rather an alien spacecraft. The unusual properties of Oumuamua, particularly its non-gravitational acceleration, support this idea. Typically, comets accelerate due to outgassing, the release of gas and dust as they approach the sun and heat up, but no such outgassing was observed with Oumuamua. Therefore, for those who believe in the possibility of extraterrestrial life, it is one of the most fascinating ideas. Dr. Michio Kaku, a well-known theoretical physicist, suggested that Oumuamua was ejected from a distant star during a supernova explosion. According to billionaire entrepreneur Elon Musk, the object might have formed when two celestial bodies collided and melted, resulting in its unique hybrid shape. Initially, astronomers were excited to find that Oumuamua's trajectory appeared to be aligned with Vega, the brightest star in the Lyra constellation, known for its debris disk. Calculations suggested that Oumuamua might have taken about 600,000 years to reach its current position from Vega. However, this theory quickly fell apart when it became clear that Oumuamua's path had changed during its journey. Astronomers concluded that it must have passed close to a new star system before entering our solar system. Its speed was similar to that of nearby stars, increasing the likelihood that Oumuamua had been traveling through the Milky Way for billions of years before crossing paths with our solar system. Another interesting theory suggests that Oumuamua is a piece of nitrogen ice. Researchers Alan Jackson and Stephen Desch of Arizona State University proposed that it could be debris blown off a Pluto-like object by a massive impact. For this theory to hold, Oumuamua would have to be much smaller than previously thought. Despite this, the nitrogen ice theory has gained traction. One of the most significant discoveries made shortly after Oumuamua's detection was that it was traveling in a hyperbolic orbit, a boomerang-shaped trajectory that strongly indicated it was not native to our solar system. Instead, it was just passing through and would never return. This revelation led to speculation about its future visibility, with many believing that Oumuamua would disappear into space, never to be seen again. But Oumuamua would defy all odds and prove most theories wrong. However, the object's behavior defied expectations. One particularly notable feature was its unexpected increase in speed as it approached the sun. While gravitational forces from large celestial bodies like planets and stars can speed up smaller objects such as comets and asteroids, they couldn't fully explain Oumuamua's acceleration. The object's speed reached 54 miles per second, 87 kilometers per second, about 3 times that of the average comet in our solar system. This anomaly prompted experts to reconsider their initial classification of the object as an asteroid, leading many to speculate that it might actually be a comet. Recently, Jennifer Bergner, a chemistry professor at the University of California, Berkeley, and Daryl Seligman, a postdoctoral fellow at Cornell University, suggested a new explanation. They proposed that Oumuamua's acceleration could be due to outgassing driven by unfamiliar processes occurring outside our solar system. According to their theory, while Oumuamua traveled through interstellar space, it was exposed to cosmic radiation. This radiation might have released stored hydrogen trapped in the object's icy structure. When Oumuamua entered the solar system and warmed up, this hydrogen could have been released, providing the force needed to explain its acceleration. Their calculations indicated that the outgassing of hydrogen might account for Oumuamua's movement. Decades of experiments support their idea that high-energy cosmic rays can break hydrogen molecules from water ice, storing it within an object. Seligman claimed this explanation is simpler and more plausible than previous, more speculative theories, such as Oumuamua being made of hydrogen ice or some exotic material. However, not all scientists agree. Harvard scientist Avi Loeb, who had previously suggested that Oumuamua might be an alien spacecraft, disagreed with Bergner and Seligman's theory. Loeb argued that they overestimated the amount of hydrogen Oumuamua could contain due to an error in their temperature calculations. According to Loeb, there wouldn't have been enough hydrogen to cause the observed acceleration, leaving the mystery unresolved. With Oumuamua now out of reach, we may never know its true nature or chemical composition. Seligman remains hopeful that more interstellar objects will be discovered soon, giving astronomers more chances to study these visitors. The next generation of telescopes, expected to be operational within the next decade, could greatly advance this research and help answer questions about interstellar objects. As scientists debated Oumuamua's origins and behavior, they encountered a new surprise: the possibility that Oumuamua isn't alone. Recent findings suggest it might have a companion interstellar object. This discovery raises new questions. What could this companion be, and did it play a role in Oumuamua's strange journey to our solar system? Could it signal a new era in our understanding of cosmic events, or does it hint at something more ominous? Some scientists have proposed sending robotic probes, equipped with sails, to intercept and study Oumuamua more closely. These missions would take decades to reach the object, and could shed light on whether it contains any signs of extraterrestrial technology or evidence of past cosmic events. The idea of interstellar probes is reminiscent of the Starshot initiative, a real-world effort to send tiny spacecraft to nearby star systems. Could Oumuamua be the precursor to such efforts, a hint that our future as an interstellar civilization is closer than we think? Stay tuned as we continue to explore this mysterious cosmic visitor and unlock the secrets of the universe. Many researchers argue that this idea is purely theoretical and lacks substantial evidence. In 2021, a letter published in Astronomy and Astrophysics dismissed the feasibility of interstellar travel, citing the immense cosmic timescales involved in traveling between stars. The authors concluded that Oumuamua is more likely a natural object, possibly an unusually shaped rock, rather than a probe sent by an alien civilization. Other studies supported this natural explanation, pointing to hydrogen outgassing as the most probable cause of Oumuamua's strange acceleration. On March 22, 2023, researchers presented findings indicating that as Oumuamua passed through the inner solar system, it likely released hydrogen trapped within its icy body, mimicking propulsion from an unknown source. Despite these explanations, the Pentagon has intensified its investigation into unexplained aerial phenomena within U.S. airspace. Since its establishment, the All-Domain Anomaly Resolution Office has launched over 360 new investigations into reports of unidentified objects involving U.S. military personnel. Approximately half of these cases have been attributed to balloons or other known objects, while the other half remain unresolved due to insufficient data. To uncover the mysteries of interstellar space and investigate objects like Oumuamua, humanity needs a deeper understanding of dark energy and other cosmic phenomena. The idea of sending a spacecraft to chase this mysterious object is exciting but presents significant challenges. For instance, Oumuamua, moving at extraordinary speeds, will pass beyond Saturn's orbit in 2 years. With a hyperbolic excess velocity of 5.5 AU per year, this mission would be unlike anything humanity has attempted. Even our fastest spacecraft cannot match these speeds. So what kind of vessel could undertake such a mission? Should we rely on advanced technologies like solar sails, or explore more speculative propulsion methods like wormholes? As we consider these technological challenges, it's important to recognize that humans are unique among Earth's species in their desire to explore space. Most animals on Earth, from birds to reptiles to fish, have no concern for what lies beyond their immediate surroundings. Even among intelligent species like whales, the concept of space exploration or communication with extraterrestrial life is entirely foreign. This raises an intriguing question. If Earth's intelligent species largely ignore space, what does this suggest about potential extraterrestrial civilizations? Could they, like Earth's creatures, be indifferent to the broader cosmos? This ties into the Fermi paradox. Given the universe's 14 billion-year history and the fact that humans have only recently acquired technology to detect alien signals, it's conceivable that we're just beginning to scratch the surface. For all the radio waves and communications we've sent into space, the vastness of the universe makes them seem like a grain of sand thrown at a distant mountain peak. Despite this, scientists remain hopeful that extraterrestrial civilizations exist, which is what the Fermi paradox addresses. It highlights the conflict between the high probability of extraterrestrial civilizations and the lack of evidence for their existence. With over 400 billion stars in our galaxy, many potentially harboring habitable planets, it seems likely that intelligent life should have arisen elsewhere and developed interstellar travel. Since many stars are billions of years older than our Sun, such civilizations should be far more advanced. Yet, no strong evidence has surfaced. The Fermi paradox questions why we haven't had any contact, leading some to suggest that our search is futile, with critics arguing that unless extraterrestrials make themselves known, there's little reason to continue funding programs like SETI, Search for Extraterrestrial Intelligence. The paradox was named after physicist Enrico Fermi, who famously asked, "Where is everybody?" during a casual conversation with colleagues. His question, often misunderstood, essentially asked, if extraterrestrials exist, why aren't they here? Despite advancements in technology and a deeper understanding of the universe, we still lack a satisfactory answer. While scientists have refined estimates regarding the number of galaxies, stars, and habitable planets, the vast unknowns persist. For instance, while we can theorize about the likelihood of life forming on other Earth-like planets, there is little data to support these predictions. The existence of life on Earth does not guarantee that it will occur elsewhere. Many attempts to solve the Fermi paradox range from mundane to extraordinary. Some suggest that civilizations are too far apart or lack the technology to communicate across such distances. Others propose that advanced civilizations intentionally remain silent, either to avoid detection or because they aren't interested in exploring the universe. The dark forest theory, which speculates that intelligent civilizations stay hidden to ensure survival, presents a particularly unsettling view. In a universe with limited resources, revealing one's existence could lead to annihilation by a more advanced species. This theory assumes that extraterrestrial life would think similarly to humans, prioritizing survival and competition. However, alien intelligence could be so different from ours that we may not understand its motives or methods. Another hypothesis posits that humanity might be one of the most advanced civilizations in the galaxy, and other civilizations are simply less technologically developed. If an alien species is just a century behind us, they may have only been transmitting signals for a short time, and those signals may not have reached Earth yet. In 2019, amateur astronomer Gennady Borisov discovered a new interstellar comet, named 2I/Borisov. This comet, traveling at an astonishing 93,000 miles per hour, became only the second confirmed interstellar object after Oumuamua. Unlike Oumuamua, 2I/Borisov was easily classified as a comet, with a visible tail and a familiar reddish hue, offering insights into the diversity of interstellar objects. Observations of such objects continue to fuel theories about extraterrestrial origins, and even the Pentagon has speculated about the existence of an extraterrestrial mothership within our solar system. Among the most fascinating cosmic phenomena are black holes. These form when massive stars collapse under their gravity, creating regions from which even light cannot escape. Black holes are thought to number in the millions across the universe, and our own Milky Way galaxy contains an estimated 100 million. Once considered distant objects, recent discoveries have brought them closer to home. For example, Gaia BH1, a black hole only 1,600 years away, was discovered using data from the European Space Agency's Gaia spacecraft. This discovery, 3 times closer than any previously known black hole, offers a new opportunity to study these mysterious objects. The Gaia spacecraft's ability to track multi-star systems has made it a crucial tool in revealing new cosmic phenomena, such as nearby black holes, further enhancing our understanding of the universe. We are on a collision course with our neighboring large galaxy Andromeda, a system of several hundred billion stars. This collision will lead to a mutual descent, altering both galaxies in significant ways. The Andromeda galaxy, historically vital in showing that the universe did not revolve around us, has been the focus of astronomical study for over a century. It was Andromeda that proved the Milky Way was not the only galaxy, shifting our understanding of the cosmos. While much has been learned from Earth, advancements like the James Webb Space Telescope have provided new, shocking insights about Andromeda that we didn't foresee for an entire century. James Webb Space Telescope just received a terrifying signal from the Andromeda galaxy. Just over 100 years ago, the Milky Way was perceived as a faint band of light across the night sky due to limited technology that prevented the discernment of individual stars. Various beliefs about the Milky Way centered it in creation. This changed in the early 17th century, when Galileo Galilei used his telescope to observe that the Milky Way was not just a band of light, but a vast collection of stars, planets, and celestial objects. Galileo's work debunked the notion that the Milky Way was the center of the universe, revealing it as a sprawling expanse of stars. In 1750, English astronomer Thomas Wright hypothesized that the Milky Way was a flat layer of stars, including our solar system, a theory limited by the technology of his time. By the early 1900s, significant advancements were made in astronomy. In the 1920s, Edwin Hubble used the Hooker telescope at Mount Wilson Observatory to demonstrate that distant nebulae, including the Andromeda galaxy, were separate galaxies with billions of stars, fundamentally transforming our understanding of the universe. The Andromeda galaxy, also known as M31, has been observed since at least the 10th century, when Persian astronomer Abd al-Rahman al-Sufi described it as a small cloud. Al-Sufi's keen eyesight allowed him to identify Andromeda without telescopic instruments, a feat possible because Andromeda is one of the few galaxies visible from Earth's surface without special instruments. It wasn't until 1612 that Simon Marius provided a telescopic description, laying the groundwork for future astronomers. In 1764, Charles Messier catalogued Andromeda as M31, furthering its recognition. A major leap in understanding Andromeda occurred in 1864, when English astronomer William Huggins studied its spectrum, finding it different from typical gaseous nebulae, which was a pivotal observation. Andromeda is massive, with a mass estimated to be between 1 and 2 trillion times that of our Sun, and is thought to be about 10 billion years old, suggesting a complex history of formation through the merging of smaller proto-galaxies. Previously, astronomers thought Andromeda was significantly more massive than the Milky Way. Recent research has revised these estimates, showing that the masses of both galaxies are much closer than previously thought. The Andromeda galaxy's physical dimensions are larger than the Milky Way. 1,000 to 175,000 light years, highlighting its vastness. One of Andromeda's fascinating features is its active galactic nucleus powered by a supermassive black hole with a mass between 110 to 230 million times that of our Sun. Observations using advanced telescopes like the Hubble Space Telescope showed 2 points of concentration in the Andromeda galaxy, with the brighter one slightly off the true galactic center, indicating intense gravitational interactions and the